Welcome to Introduction to Robotics. As I've mentioned before, my name is James Conrad, Professor of Electrical and Computer Engineering. My area specifically is embedded systems, but I've been working with, I don't know if I mentioned this before, I've been working with robotics for, I gotta count the years, since '93, so that's what, 19 years? And the first robots that I was working with, as you saw, with little micro robots, taquito. But I've expanded that into everything, including the Zapata bot, which we saw in last class. Remember Zapata bot? That was the vehicle that kind of drove on its own. Hey, just for grins, I always like taking some time and looking at some videos, so let's look at these. Don't you know, volume's not working. As you can see, this is a Boston Dynamics vehicle. Actually, I believe iRobot has one that's even similar. But the important thing I want you to take a look at is all aspects of this. Locomotion. What does that locomotion look like?
Insect,
Yeah, it's kind of insect-like, it's kind of leg-like, but doesn't it look a little bit almost like flippers or something?
It's like what they use for the prosthetic legs, right?
Yeah, very similar to what they use for a prosthetic leg. What's the other prominent thing you notice from that?
It flips over, you flip it back over.
All right, it flips over. I'm thinking more of the assembly of it. It's got two of them. They're in the back. There's two antennas.
Yeah.
Right.
So what do you think? Is that autonomous or is that controlled by some sort of remote control person?
Remote control.
I think this is controlled remote control. Interesting that this is so watertight that it could go in water, and in fact, by putting flippers on it instead of the legs, it can go underwater.
Pretty awesome.
Now this is an interesting thing. You notice what it has trailing behind it.
Wire.
A wire.
A leash.
A leash. Why is that?
Someone was underwater.
Why isn't it using wireless?
Doesn't work underwater.
Doesn't work in the wire.
All right, why doesn't it work underwater?
Refraction.
All right, radio waves do not work underwater, except for maybe about a distance, maybe a centimeter or so.
Huh. Terrible.
What do you think? I tell you what, look at that. That thing is hauling.
Doesn't go too straight. It kind of just hits the ground and goes whichever way it can.
It's like a little dog.
But that's just one of the many introductions of robotics. And one thing I should point out is, as we've discussed before, there's all aspects of locomotion, all aspects. In fact, let's take a look at some of these, or let's identify some of these that we had discussed or that you could think of. What do you think are the some of the important locomotion that you're going to get with robotics? So, locomotion, what do you have?
Wheels,
Wheels,
legs,
Legs.
Treads.
treads,
Wings and propellers.
tracks, I guess, right?
treads, tracks,
Helicopter,
Air.
So what kind of air?
Wings.
So you're gonna have wings with some sort of propulsion. Did I get that right?
You got the R.
Did I get it? Say it again?
You got the R.
Yeah, that would be helpful, wouldn't it?
You misspelled treads too.
Did I really?
Yeah.
Oh, sh.
EA.
There we go.
Treated.
Wing, propulsion, what else?
Propellers.
Propellers. Two L's or one?
L.
Two of them.
Yes.
Man, now you know why I don't like to write too much. Propellers. This could be anything like a copter, quad rotor, anything like that. What else?
You the motor.
What kind of, what aspect of motor?
Rotate. A DC mode.
We'll put it out there, maybe we'll address it later. What else?
Flaps.
Flaps?
You said flaps for legs.
Oh, flippers, flippers. All right.
Flap.
You know, you say flaps, and I'm thinking airplane. What else do we have? Oh, there's lots more.
Are you just talking about aspects of locomotion?
Yeah, any aspect of locomotion.
Like size? Yeah.
No, I mean, I think of more like a mechanism. How about muscles?
Oh, a belt. I guess. I heard it was
Did you say belts?
Yeah.
All right.
Magnetics.
What did you say?
Magnetics. Air.
Years.
Now we're getting into specific technologies.
Bearing.
Slither, swim,
Actuators.
well, actuators, just general everything. What did you say up here?
Bearings. Like
Bearings, we're getting into details.
Gravity.
Say that again?
Gravity.
Gravity, that's a tech, or that's a law of physics. I think we got enough here. Right? Oh, by the way, there's also jumping. So from that respect, we have springs. And I have an example of a robot later of a small device that will actually hop
I think I know which one you're talking
about 3 stories.
Yeah, that's one I know.
It's somewhere between 20 and 30 feet. It's amazing. It's about, yeah, it's about this big or so.
Yeah.
And so we'll show examples of that in the class. Which should make you all scared because these things are going to be spying on you later, right?
They already are.
So again, to recap what we said earlier, what are the important aspects of any robotic system? Remember I showed this.
Move it up a little bit. There you go.
Oops, wrong. And that was?
Power.
Sensors.
Control on brain,
Brain.
actuator, and power.
That's actuation. And by the way, power can probably go to all of these, right?
Yeah.
And so if we're talking about locomotion, where does that fit in here? Which one of these blocks?
Actuation.
All right? So all of these are the actuation. So if we start thinking about other things here, let's look at sensors, right? So if we want sensors, what do we have?
Infrared.
Temperature sensor.
Ooh, I'm gonna see if I can even spell this. Infrared. Did I get that right? Except usually it's capital R, right?
Sound. Temperature.
Same distance.
Well, how do you determine
Sonar.
distance?
Sonar.
Sonar.
Ping.
Hall effect.
Say that again?
Hall effect.
Hall effect.
Touch.
Light.
Light.
Pressure.
RF.
Temperature.
What's RF?
Radio frequency.
Radio frequency.
Magnetic.
Say that again?
Magnetic.
Let be electrical too.
I want to say they done something in smell.
Flow sensor.
I'm not sure exactly.
Actually, sensors that can recognize odors is a really cutting edge technology because the eventual creation of a human or humanoid is going to have to include all the senses. Touch is easy. What else is easy that's currently being done?
Sound.
Sight.
Sound. Sound.
You've got sound. What else?
Taste.
Taste.
Is that easy?
Is there anything that does taste? Well, what determines taste?
What the
Brain synapses.
Say that again?
Like your brain synapses.
But what on your tongue detects that?
Taste buds.
Taste buds, and what do they detect though?
Acid.
All right?
pH.
So now acid means pH.
Yeah.
Whoops. I was writing it like
That's with
PhD.
taste, isn't it?
Say that again?
You're saying that's with taste, right?
Well, pH is one of the things that taste buds actually detect. And there are pH sensors. There are other sensors that also detect gases. Things like O2. Think about this. Your automobiles have that, right?
Yeah. O2 sensor.
As well as CO2 sensors to detect how rich your engine is running. So these are some pretty
Those
typical
detect the
sensors.
pressure, though.
Say that again?
Those detect the pressure.
Are you sure?
Well, smoke detector. That's is that right?
Well, smoke detectors. Well, what do we use for smoke detectors?
Isn't that
Hammer,
checking for mercy levels?
That's usually particles, right?
Yeah.
So it uses a combination of light, I believe.
Oh.
But getting back on gas sensors, I've got some examples of gas sensors in my lab that I'll pull out and we'll take a look at later. They're rather expensive. They're like an O2 sensor is $50, the CO2 is $75.
What about UV?
Oh, UV? Oh, that we'll put that under light. Do we have light?
Accelerometer.
A gyroscope.
Yeah, gyroscope.
How about an electric field sensor?
Fuel sensor?
Field.
Oh, field.
Magnetic.
How about magnetic?
The electric.
Oh, you're saying
Magnetic.
current.
Two different things.
Yeah, current. Voltage.
Gyroscope.
Gyro?
Yeah.
Yep.
By the way, that's under a general class. IMU. Everybody know what that is? Inertial Measurement Unit. Oh, in fact, I'll even write that down. A typical inertial measurement unit will detect acceleration in 3 dimensions, will detect, we'll use a gyroscope in 3 dimensions as well, to be able to identify pitch, roll, position, gravity, forces due to acceleration, in any one of the directions. And then IMUs also are more and more including magnetic sensors, in other words, to detect compass direction. There's another one that is kind of a sensor, GPS.
Well, something that detects colors.
Ooh, that would be
Okay.
light UV.
Yeah.
And in fact, do any of your Lego Mindstorm kits have the color light sensors?
They should.
Isn't it built
The
in?
newer ones do, the older ones don't.
It doesn't appear to do it, we tried.
Okay,
Uh,
they're an upgrade.
What about piezoelectric?
Piezo, that would be, I think Piezo looks at voltage.
Read all the waves up there, like radio and Wi-Fi and all that.
Let's see, I just put a general RF.
You have weight up there?
Which one?
Weight?
Weight? Weight would be,
Force, mass.
that'll be 4.
strain.
Yeah.
Anything else?
Speed? Speed?
Speed.
Speed, velocity.
Well, speed will be something you measure from one of many things, including Hall effect sensors,
Like radar.
light as it detects how frequently something is going in. Radar is oh, that's one thing that was not mentioned.
Sonar.
LiDAR. Sonar is up there.
Yeah.
Okay, we got enough. That's a nice set. But now look at control, right? So if you think of all the aspects of robotic control, what's the underlying? Oh, maybe we should step back and say what determines what a robot is. What does a robot need to have?
Purpose.
Howard.
All right. So what does a robot need to have?
Remote control arm.
Everything we talked about yesterday.
I didn't talk about anything yesterday.
Tuesday.
Whatever. Days run together.
Yeah, I know, right?
Same difference.
All right. So we know several things for sure, right?
Power source or energy source.
Power source
Microprocessor.
and a.
Microprocessor?
Say that again louder.
Microprocessor?
I'll call it control.
Controller?
Mechanics.
What kind of mechanics?
Make a move. I mean,
Okay,
you-
so some sort of locomotion. Does it need sensors?
Doesn't have
No,
to.
it doesn't need that.
How about a structure?
Yes, it does.
Because if
It
you think about it
does.
like a robot, you could just
It does
turn it
have.
on and just go straight.
Well, let's look at
It's
some of
something
the
to
things that we have. Give you an example.
I think it does not.
My professional organization, the IEEE, had a robot competition. And the objective of this robot competition was to create something that would run around in a field that was 10 feet by 10 feet, artificial turf, and pick up trash. Particularly, they gave it the objective of empty soda cans, empty soda bottles, and soda bottles made of plastic and soda bottles made of glass. So the objective of that would be to pick them up and put them in a bag. That was the intent. Lots of robots out there that would go, and oh, by the way, if you sorted them between the 3 types of trash, you got extra points. So there were ones that went around, the one from our university that I thought was really innovative. They got the award for the most entertaining robot because it would run around, and as soon as it found something, it would go up to it, and then it would have these whisker arms, and it would go swish, 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 swish. and try to bring it into itself and then put it into a bag. And it was entertaining because I guess they liked the way it just kind of waved its arms. The number 7 robot did nothing more. Oh, by the way, also you would lose points, and lose lots of them, if you touched the edges of the competition field.
Mm.
And you can start and stop your robot at any time, and at the end of, I think it was 3 minutes, would be the end of your run. So one team from a university, and should I mention the university's name?
Go for it.
Yeah.
I think it was either Virginia Commonwealth University or Virginia Military Institute, one or the other. Looked around at the field and took their robot, which was nothing more than like a Lego set of wheels with a piece of wood that had duct tape on it. Sticky side out, sticky side out.
That was
And they would
like
place it down, and they would push the button to go. And they would run over to the other side, and before it hit the edge of the playing field, they would turn it off. All right? So, and by the way, that's all it did. All right? That's all it did. It would go straight. But by lining it up, they would usually get 3 things to stick to it. All right? 7th place out of like 45.
wow.
Is that a robot?
Wow.
Yep, and it had no sensors. Completely. It just rolled through.
It had no sensors. It had locomotion. It did have control because it started the motors when you pushed a button.
And it stopped. When you
Wow.
It only stopped when you pushed the button.
That's still control. You hit the button and it stops.
All right? So, was that a robot?
Yeah.
No.
Yes.
All right, let's take a vote. Who says yes, it was a robot?
I said yes because it wasn't the competition. Otherwise, they will kick him out.
All right? Who says no? Okay, so think about this. I have a car. I turn the ignition on. It goes, and then I pull it into drive, and it goes for a while, and then I press the brake and I put it back in the park. Is that a robot?
Yeah.
Yeah.
By your definition, it is. Right?
What about all the other
Yeah.
variables that are going on?
So maybe we need to tighten up our definition of a robot. First of all, does a robot need to move?
Yes.
Yes.
Oh,
No,
okay.
it can just think.
Does it need to be mobile?
Yes.
No, it can just think.
No, think of the robotic arms like in the car factory.
Yes, they do.
Well, they don't
know.
like still move.
They still move back and forth.
Foreign mobile.
That's the mold.
All right, I mean, does a robot need to move? If I set a robot down here and I start it running, does it actually have to move from this position to over there?
No.
All right. You think it does?
No.
Oh, okay.
I got an awesome example.
Okay, give me an awesome
Remember
example.
back in like the late 80s, early 90s, the first Nintendo Entertainment System had that Roby the robot that sat there and was your second player. It just sat there. It had 2 sensors that picked up what was going on the screen and it played video games with you. And it didn't move. It was awesome.
Well, we know he didn't have
Well, that's all right. My son had a robot toy that would sit in the closet and turn itself on. All right. Was it truly a robot, or actually was it a possessed toy? I don't know. All right. That's an interesting definition. So, but it didn't move. But it had. Did it have some motion? Did it at least touch?
I think his head turned and maybe and
So I guess we need to identify what defines a robot. What does the book say?
We don't have it yet.
I don't have that.
All right. What does the book say?
They were out of it at Grace.
Oh.
That's what I think.
It's been chipped.
Say that again? Oh, they pull out the book. That's good to see. And he's got one, and I can see the receipt says Grays.
They
There's
were
like,
out when I went today, so.
I bought,
Yeah, I got mine
there's
back
one of
last
2
year, so.
when I went.
There's like 6 in Charlotte.
There's 6 in
There's
Charlotte.
like 6 at or like 4 or 5 at.
How much was it?
It's like 50 bucks or
59.
something.
59 and at Gray's it was,
Like 55 or something.
you say $4
almost
going to Gray's.
I'm
Too
saying
bad.
much more.
Um,
I'm saying
eBay.
$10.
Or you can go online and buy it for $10. All right, so the definition from the book says, this is important because think about, if you talk about a field, you actually have to define what it's going to be. So for all intents and purposes, in some definitions, the laptop sitting on this table right here is a robot. It's got a control system. It actually has sensors. It's got some moving parts, hard drive,
Solid state.
solid state. So we have to define what the robot does, or what it is. Does it have to do anything? Does it have to have any motion?
It has to serve a purpose.
All right, let's say it has to serve a purpose. I'll live with that definition.
So if you find the definition.
Yeah, but it talks about, the book's focused on mobile robots, so.
Yes, it's mobile robots.
Yeah.
So obviously mobile robots are gonna be ones that move.
Okay?
But this also says mobile robots, so it's probably not gonna give you the definition of robots, it's probably gonna give you the definition of a mobile robot.
Yeah.
All right? So I'm going to offer the following definition. I'm going to offer that it has autonomous control.
Yes.
Autonomous could mean anything from you pre-program it and then it does something on its own.
Alright.
Whether it be moving around on the floor, or in the case of manufacturing robots, it will repetitively do some sort of action. All right? I'll show some pictures or some videos later on of a robotic system that will pick up and move baked bread from one place over to another place and then put it in bags. And in fact, most of the robots in the US, and I would bet in most of the world, is associated with manufacturing. You've seen the videos of automobile plants painting and welding. Yes?
So, are you familiar with Raytheon?
Raytheon is a company, yes.
And they're trying to build an exoskeleton, so that would not be a robot.
No.
All right, so if you think about what he's saying, an exoskeleton is basically a machine that will assist me.
Yeah.
All right? So does it do anything on its own?
No.
All right? Would you call that a robot?
No, but they're trying to make it to where you can like get out the suit and then it works on its own.
But it enhances, to an extent, it enhances your motions. Like, you go from being able to lift a 20-pound weight to a 400-pound weight.
How's that autonomous control?
So, I mean, it's an assisting robot. I don't know. I
An
mean,
automobile assists me to go faster. Does that make it a robot?
I think so. My car,
Okay.
I can floor my car and set it on cruise control, and I can't crash into a wall. It'll slam on its brakes by itself.
I'll show the Darwin video on that one.
No, like really, parallel park.
Okay, there we go. There's a good example. Parallel parking. How many of you are familiar with the technology now to
Yeah.
some automobiles to help you parallel park?
Yes.
All right. Does that mean it has autonomous functionality?
Yes.
Yes.
All right.
You go up, and it
Yeah,
tells you how far to park up on the car, and then you take your hands off the wheel, and you press a button, and it spins the wheel for you, and then spins it back the other way.
All right.
Yeah.
So I would say yes. And by the way, I'm working in the field where automobiles are autonomous. In other words, they are autonomous robotic vehicles that will drive you from the parking deck over here to home without me doing anything other than looking at my iPad.
They are to an extent now. Like
Yeah.
in my dad's new car, I can't jerk the wheel to the right if there's a car next to me. It won't.
Yeah, exactly. It will align itself. Into
All right, so
Because it's got sensors on the side, so it won't let you move the wheel that way.
So there are technologies now that we're putting into automobiles that will make it autonomous, but would you call it a robot because it's autonomous all the time?
I mean, it's not autonomous. Nothing's autonomous all the time.
Okay. But there are some vehicles that are. For example, Google has some vehicles that will literally drive itself.
Do they turn themselves on and off?
Is that a requirement for a robot
No.
to turn itself on and off?
You
Then
said
it can't be-
autonomous all the
that's not
time.
full
That would be
autonomous.
all the
That's
time.
autonomous after you power it on.
After you power it on.
Yeah.
All right, so I'll call this the definition. Autonomous control when operating. After power on.
We say fully autonomous?
I'll say fully autonomous. Without human interaction. So when I showed my Zapata bot the other day, as it was driving around, was that a robot?
No.
No.
No, because it was still being controlled by somebody. When we just looked at that RHEX, the little vehicle running around, was that a robot?
No.
No, really, that was a radio-controlled vehicle, right?
Yeah.
When we saw Big Dog in our last class, was that a robot?
Which one?
A fake one?
The real one, right? Not the one that was two people, all right?
How is he controlled? I mean, how does he know where to go? GPS?
He doesn't, he just goes straight.
That is also radio controlled.
Is it okay?
They are working on it to be
GPS?
GPS guided,
Okay.
all right? So if it's GPS guided and you give it a beginning point and an end point and it walks from here to there, do you think that's a robot?
Yes.
Okay,
Yeah, sure.
so we'll agree autonomous control when operating. All right?
Okay.
Serves the purpose, autonomous control when operating, and I don't, one thing that we didn't actually add in here, but I am, is motion of some sort. This is a really broad definition if you think about it, right?
Yeah.
And to be honest with you, things change as time goes on. If you've heard the phrase artificial intelligence,
Yes.
back in the 50s, a compiler for Fortran was considered artificial intelligence. All right? Nowadays, there are certain technologies that are just assumed just to be a part of the regular operation of computers that are no longer artificial intelligence. The ability to turn on and off a fan when it gets too hot used to be artificial intelligence. So, let's go with that. How about that? So going back onto our general system and the definition. We're going to talk a little bit about control. And how many of you have had a controls class before? Raise your hand high so I can count. Oh, quite a few, all right? So I'm going to do a really, really, really simple control system. So what do we usually have with respect to a control system? Feedback. Feedback.
Negative feed.
So we'll say we have feedback sensors. And so what would this be?
Transfer function.
Our control. Or I should say our controller. And then we would have our controlled system. This should be in your book, by the way. We have output. And our output is going to be measured by our feedback sensors.
Input also.
And, by the way, we also have input.
Which are gonna be the sensors.
But what we expect is that there will be some sort of error as you control what the feedback says is happening and what the input says should be happening. And the difference in that is going to be the control. and then the controller will adjust. Let's take an example. If we have just a regular controller like your little, does anybody have one of their Lego Mindstorms already built for line following?
Well, I don't.
I mean, it won't work.
Yeah.
Even if it doesn't work, I just want to show it. Is that it? All right.
We don't have one.
So it might have a few things that it needs to do. So here we go. This is a. Oh, is this going to hit something?
Yeah.
Oh, cool.
Destroyed.
So, by the way, for those looking at this in TV land, lab number 0 was to take a Lego Mindstorms device and do something cool that we could show middle school kids. And so this is a line-following robot. It's going to have a light sensor down here, which means it has an LED light and a light detector of some level. And it's working on the reflection of light off of the surface. Black will give you a certain level, really high reflection. White will give you another one. Gray will give you some measurement in between. So if this is our actuation, our motors, our controlled system, and if this is our feedback sensor, by the way, this entire thing is our controller. And so our input will be, I expect the sensor to read black. And the controller will make adjustments to see, is it black or is it not black? Well, in this case, the controlled system is moving forward, and when you go off, when I say black, usually we put down a strip of electrical tape on the floor. All right? And if it goes off of the black electrical tape, then the sensor will detect something else. So in that case, the feedback sensor, when it detects white, says, I expect black, I see white, so my error is that somewhere between the last movement and this movement, I am no longer seeing what I'm supposed to see, so I need to make a motion. I need to do something. And it could be, in the controlled system, it could be move this wheel forward just a little bit faster than this wheel. But whatever it is, it's providing feedback, and hence why this is a good system of controlling robotics. Now what if I didn't have a feedback sensor? This would be what we call open loop. So because we have feedback, it's called closed loop. Does a robot need to have a closed loop
Yes.
environment?
Yes.
Yeah.
You think so?
Yes.
Yeah, it's autonomous.
Does it have to?
I mean, when you do something, like personally,
If you never gave it feedback, it would just keep switching to whatever the next step was, and then finally just be done with it.
All right, so let's look at an example. By the way, if you, do I trust to hand this back, or shall I just go here?
He will take the call.
So, let's imagine a pick-and-place robotic arm. And you program it to always go, pick up here, put down there. Pick up here, put down there. Pick up here, you get the idea.
Look, can you do it a couple more times?
I can get it. I'm gonna make you do it. Do I need feedback for that?
It depends.
Eventually,
You need
until you have it.
Is it helpful?
Yes.
Okay, so in our definition, it doesn't require closed loop, but closed loop is really helpful, because it would be nice if you had sensors at the end of the fingers picking up the part to be able to say, oh yeah, I've got something there now, and I'm going to put it down over there. So this is a closed loop. So the recommendation is that you have a closed loop system for your robotic, and in fact I required that. I said that you needed to have both sensors and actuators motors. I see one of our class people are going to be looking for a ball, and once you find it, kick it or something like that?
No,
Or?
it will. it will see that there's an object in the way of the line, and it will kick it out of the way and continue
Okay.
going.
Just get
It'd
away.
be really cool if it picked it up. and
Get
flew.
away.
Now, what would be really cool is if you had a soccer playing robot,
They
right?
have they're pretty flamethrower attached. to the side.
Flamethrower attach, jet black. All right, let's go on.
This is not like that.
The last thing I'm going to cover today is, I've got just a few more minutes, and that is to just think about when you're writing control software and what has been said in the past for how to ensure safety of robotic systems. So for this, we're going to look at a science fiction writer. Is that in this book? It was in the other one that I used.
Is that Wolf? Newton?
Isaac Asimov. Everybody familiar with that? Him? iRobot, Foundation series. He was really into humanoid type robots. And he came up with 3 laws of robotics.
From the movie?
Mayor's Montana.
And number 1 is basically never harm a human.
Is he Mold?
More.
Yeah, sounds like it.
It is in there?
Yeah,
Okay.
it is.
Number 2 is obey humans. Unless
It's to harm someone else.
Constitution number 1.
it violates law 1. And then number 3 is do not harm another robot. Unless it would violate laws 1 and 2. Now, oh my gosh, you'd think it's the end of the world. Philosophers and computer scientists and engineers have debated the 3 laws of 3 Isaac Asimov laws of robotics for years and years and years. They've been added corollaries onto this. They made it look like lawyer speak for each one of these things. But there are other aspects of robotics associated with ethics that we will actually cover in this class. So later on we'll talk about, for example, robotic toys, or the use of robots to care for the elderly. And some aspect of that, you can just think about what are some of the problems that will come up with this. What if you have robots take care of grandma, and then nobody pays attention to grandma other than the robot? Is that ethical? So that is one thing that we're going to be investigating later on in the semester. So this is it for our introduction to robotics. We will start getting into the technologies in great detail in our next class. That is it. Thank you very much.